So this morning we're talking about logical expressions. And we're moving away from your familiar world of real numbers, and we're shifting instead to a world where the basic elements are statements instead of numbers. And statements are things which are either true or false. So instead of addition and multiplication, we have and or. And instead of putting a minus sign in something, you put a not in front of something. So in what follows, we'll use the Python notation for and, or, and not. And conveniently, Python just uses those English words. So if you've read the textbook, and I assume you all have, you know the technique of truth table. And this is the way things were done 50 years ago and are really still pretty commonly done today. What we're going to do is shift into Python, and the heart of what we'll do will rely on a list of truth values, true and false. Those are the only two possible truth values. So to show how this goes, we'll use a for loop iterating over truth value list to display the truth value for negation. And just let me show you that, just to get you started. And the way we do it, for P in the list of truth values, print the value of P and then the value of not P. And this says if P is true, not P is false. If P is false, not P is true. If you do this in CoCalc, you'll get the label row lined up better. This software that I'm using puts something between the printout of the label row and the printout of the truth table. But don't let that bother you. So now I want you to use a nested for loop to display the truth table for P and Q. And this time I want you to stop the video and try to do that on your own. Okay, you're back. I assume you had a try at that. Let's look at my result. So here's the nested for loop. We run the P through truth values, and we also run Q through truth values. And that gets us the standard setup of a truth table, which is true, true, false, false for P, true, false for Q. And what we've got printed out here in the third column is the set of truth values for P and Q, which is true, false, false, false. Okay? And if you compare this with what's in the textbook, you'll see that it's the same thing. So minor change, this should just take you a few seconds. Use a nested for loop to display the truth table for P or Q. Stop the video, do your work, and come back. Okay, you're back. I assume you've done your work. And here's the result. The only difference is that it looks exactly the same. There's only one tiny change in the code. Instead of P and Q, we have P or Q. And what we get in this third column is true, 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 false. And if you look in the textbook, that's the same thing that you got for P or Q in a in the 1950 style truth table. So most of the work you do with truth tables is trying to prove that two logical expressions are equivalent. And the standard way to do this with a truth table is to construct a single truth table which contains columns which represent the two expressions. And then you look through the columns visually and compare them and note that in every row the two expressions give you the same truth value. If that's true, then the two expressions are logically equivalent. And if there's any discrepancy between the two rows, then they're not logically equivalent. So do this in Python. Don't worry about the spacing. Just look at the last two columns. Let's see, what was I doing here? So I guess I left out the question there. I wanted to, this is the same thing that we did before, not P and Q and not P or not Q. If you do those two things, you will see that this is the column for not P and Q, and this is the column for not P or not Q, and you notice that they are exactly the same. So we've just used a 2020 tool to accomplish a 1970 task, and here's a 2020 method. Instead of creating two columns, you could create two lists and ask if they are equal. Here's what I mean. You start off by creating a list for expression 1 and a list for expression 2, and those are empty lists. And then as you iterate through P and Q, you append the current value of the expression involving P and Q. In EXP1, you put the current value of not P and Q, and in expression 2, you put the current value of not P or not Q, and then you ask, is expression 1 equal to expression 2? And it's true. So this is a Pythonic trick used to prove one of De Morgan's two laws. Do the same for the second one, and I'm sure having read the text you know what De Morgan's laws are, and if not, it's pretty obvious. You just replace the and with or with and. So stop the video, come back when you're done. Okay, you're back. I assume you're done. Let's take a look at my solution. You notice that I've got the or here instead of an and here's the and instead of the or. And the conclusion is that the two are the same. So let's use this method to decide if P and not Q is logically equivalent to not P or Q. It kind of sounds like De Morgan's law, but try that out and see if these two expressions are logically equivalent. Okay, stop the video, do your work, and come back. Okay, you're back. I assume that you've done your work. Let's take a look. And here we see that here's the P and not Q. Here's the not P or Q goes into expression 2. And when we compare the lists, expression 1 and expression 2, they are not identical, so we conclude that this logical expression is not logically equivalent to this logical expression. Okay? Let's talk about some general principles. The distributive law. This is associativity. With real numbers, you've learned a long time ago that it doesn't matter in which order you add three real numbers, you'll get the same result. So if you add y and z first and then add x, you'll get the same thing as if you add x and y first and then add z. And this is referred to as associativity. So we say that addition is associative. Is and associative? We'll need a third variable, call it r. The question is whether P and Q and R is equal to P and Q and R. And do this in Python. Of course, with the third logical variable, there will have to be another level to the nesting of our for loops. But I think it's pretty obvious how to do that. Okay? So go ahead and do that and come back and look at my result. Okay, you're back. I assume you wanted to look at my result. Let's take a look at this. So here's our third level of nesting for P and TV, for Q and TV, for R and TV. We append P and Q and R, and to EXP2 we append P and Q and R, and we ask if EXP1 is equal to EXP2, and it's true. So yes, the conclusion is that the logical operator AND is an associative operator. The distributive law kind of looks a lot the same. That's why I was kind of stumbling around a few minutes ago. This is something that you've used in factoring a lot as you've learned algebra. We know that for real numbers x, y, and z that x times y plus z is equal to x times y plus x times z. It doesn't matter what the values of these variables are, this is always true. And we refer to this as the distributive law, and we say that multiplication distributes over addition. Is there something analogous in the mathematics of logic? Does and distribute over or? Does or distribute over and? First thing, check the and over or case. So go ahead and do that. It's the 3-level nested loop, and stop the video, do your work, and come back and look at my solution. Okay, you're back. I assume you've done your work. So here is, notice again the 3 P, TV, Q and TV, R and TV, so 3 levels of nesting. And we have P and Q or R, and we ask, is that the same as P and Q or P and R? So exp1, is it equal to exp2? Yes, these two lists are identical. Therefore, this is true. Yes, it's true. And distributes over or. Well, okay, now check the or over and case. Go ahead and do that. Stop the video while you do your work. It's really just a minor bit of rewriting of this code. Okay, you're back. I assume you've done your work. Yep, it's true. Doggone, there are 2 distributive laws in the algebra of logical expressions. So the code above works well, but you notice that what I have to do all the time, I get into the code and I rewrite the critical parts of it. And that leads me to ask if I could rewrite this whole thing as a function. Now, to rewrite it as a function, I have to supply logical expressions as arguments. And you can do that because Python is able to use functions as parameters of other functions. So what I want you to do is write a function compare of f comma g, where f and g are functions which return logical values. The function compare should return true if f and g are logically equivalent and false if they are not. Okay, so really this time stop the video and go to work on this. This will probably take a while because this takes some thinking. Not too much thinking, but enough to take a few minutes. Okay, you're back. So here's our function, compare. Its parameters are f and g. And you notice from internal usage what f and g have to be are functions which accept 2 logical variables as input. Although frankly, the way it looks, you could actually return anything out of these functions and it would work. It just wouldn't be testing Boolean expressions or logical expressions. And then instead of comparing things visually, what we do is we say if exp1 is equal to exp2, we return yes, equivalent. If the 2 are not equal, and that is we get into the else, then the variable conclusion gets set to no, not equivalent, and then the function ends by returning the value of conclusion. Okay, so try this out. We need 2 functions which return logical values. You can try it out with anything, but go ahead and try something. Try an example where you know the answer. Stop the video, come back here, and look at my solution after you're done. Okay, you're back. So I defined two functions. F1 is not A and not B, and F2 is not C or D. And I then call the compare function on F1 and F2, and it returns the value, yes, they are equivalent. And of course, you'll recognize our familiar De Morgan's law example. A final note for today. We notice that there's a symmetry in the distributive laws in this mathematical system. And distributes over or, and or distributes over and. Do you see the same symmetry in the mathematics of numbers? Does addition distribute over multiplication? Try one numerical, and I left out the word example, using 3, 4, and 5. So go ahead, do your work. This is just a little bit of elementary arithmetic, and come back and look at my elementary arithmetic when you're done. Okay, you're back. So expression 1 is 3 plus 4 times 5, and expression 2, this is a number, of course. Expression 2 is 3 plus 4 times 3 plus 5. This would be multiplication distributing over, addition distributing over multiplication. And the two answers are 23 and 56. So no, you have a counterexample, so this is not a universally true statement in the algebra of real numbers. So I'm getting back to my mathematical side of my personality this morning, but we're using Python to explore mathematical theories. Okay?